Hello, good people. Welcome to the first video of this new unit, Unit 3. So we're going to start with topic 3.1. 3.1, I'm going to break into two parts. Part 1 is going to be kind of the general rule of how we can apply the shortcut when we have composition of functions. Part 2 is going to be what happens when our functions become a little bit more complex, or what if I have multiple compositions in a given function. So we'll start by kind of reviewing some things. So by now, we should be able to take the derivatives of all of these functions, right? The first one is a quadratic. I can do the power rule and sum rule. The second one is a trig function. I can find the derivative of sine x. The derivative of sine x is cosine x. The fourth one, I can find the derivative of the exponential and the natural log. And then the last one, I can find the derivative of the square root by, I guess first I would need to rewrite this, but then I would be able to find the derivative using the power rule. So what we're encountering with the chain rule is we're going to be able to find derivatives of functions that look like this. Or functions that look like this. Or functions that look like this. As I continue writing, I'm hoping you can see how the right column is similar to the left column, because I'm using the functions that are pre-printed here, but I'm also introducing some new parts, right? And so as I finish this last one, oh, maybe I made it too long there. We'll do x cubed plus 3x squared. How about that? So all of these functions in purple that I just wrote that I call g of x, they're really all part of or in relation to the functions on the left, because in reality, I'm using the formula or the setup of the functions on the left, except I'm introducing a function inside where the variable would be. So just as a quick example, if I can make things more explicit here. In the original function, in the original f of x function, I had sine of x, right? My variable was x. But what if I replace my variable with a whole other function, which is what happened here, right? I'm taking the sine of e to the x. So it's not just a variable. Now I'm taking the sine of a function. So there's something inside of the sine function. And the same thing with the last one. I had the square root of x. X was my variable. But what if I replace my variable with a whole function itself? And so with all of these examples in purple, we now have composition. And if you remember, composition meant we have an inside-outside relationship to a function. So for example, I could have, I don't know, something that looks like cosine x plus 6 and everything to the fourth power. Well, cosine x plus 6 is a whole function on its own that's inside of something to the fourth power, so it's inside of x to the fourth power. And so what we're going to find here is that the chain rule is going to help us find derivatives of composition situations where we have an inside and an outside function. And so part of the practice that we're going to be doing here in this first video is, or in this first part, is identifying, can you tell which one is the inside function? Can you tell which one is the outside function? And so part of that is going to be in subsequent videos coming up here. In order to tackle these new functions, we do need to remember when we ask for dy dx, do you remember what it means to write dy dx? What does it mean to write this symbol? The symbol says we're finding the derivative of y with respect to x, meaning that I'm treating x as my variable and my whole formula is called y. So I'm taking the derivative of the y formula, the y equation, but that y equation is in terms of x. Whereas if I look at something like this, I'm finding the derivative of the u equation with respect, I'll abbreviate with respect to y. So now I'm finding the derivative of the u equation, but my variable is y. So I'm taking the derivative with respect to y. So when I look at example 1 here, and we're looking for the derivative of y with respect to t, I'm looking for the derivative of this equation, this formula, but I'm doing it by treating t as my variable, and it sure is. That's the only variable I see. So when I take the derivative, I could do this step. I usually don't show this step, but I could do the step. Let's take the derivative with respect to t of this side of the equal sign, and we'll take the derivative with respect to t of the other side of the equal sign, right? We're taking the derivative with respect to both sides. We're taking the derivative of both sides with respect to t. Because if I take the derivative of y with respect to t, I will get dy dt. And if I take the derivative with respect to t of 2t cubed, well, this is a power rule, so this is going to be 6t squared. And the derivative of a constant 4 is 0, so it's plus 0, but I guess I don't have to put that. And then there would be our answer, right? So this is still doing the shortcut rules that we learned, but we're doing it at a rate where we are using the other notation of the derivative. Okay, example 2. We're given two equations, an y equation, and we're given an x equation. Can we find d of dy dx, the derivative of y with respect to x? That would be using this formula. So let me change my color here. So we're going to find this for that. But then it also says, can you find the derivative of x with respect to t? Well, here's my x equation, and it's in terms of t. So let's find the purple part. So if I take the derivative of this side, I'll get dy dt. And if I take the derivative with respect to x, I'm sorry, this is dy dx. If I take the derivative with respect to x, then this would be 12x cubed minus 2. And then I'm going to take the derivative of x with respect to t. So this would be dx dt, which is equal to the derivative of t squared, which is 2t, minus the derivative of 3, which is 0. So this would be the derivative of that. Yes? So then how does this play into the idea of a composition? Well, what if I asked you to find dy dt? Now I'm looking for you to find the derivative of the y equation, but in terms of my variable, which is t. Well, that's not this purple formula, because this purple formula only has y's and x's. And it's not this green formula, because it only has x's and t's. However, if I were to take this whole expression that x equals and replace it wherever I see an x, then I would get y equals 3 times t squared minus 3, the whole quantity to the fourth power, minus 2 times t squared minus 3. Now I have an equation that's in terms of t and its name is y. So I can find the derivative of that, which would be what this purple, maybe I should change the color, but this is what that symbol is asking us to find. I'll do it in red. dy over dt. Now I can find the derivative of this and get that. But now it gets more complicated, right? Because now I'm looking at my setup here, and now there's a bunch of things going on. This is where the chain rule is going to come into play. This is where the chain rule is going to help us. So we have to be mindful. What is the symbol telling us? Well, it's telling us to take the derivative of that equation, which is in terms of this variable. But what if I ask you to find the derivative of that equation in terms of a variable that it's not there? Well, then I would have to somehow convert it into that variable. But in doing so, I've now created a composition which looks a little bit more complex than the previous derivatives that we've taken. So in video 2, we'll talk about the chain rule and how we can use it to help us figure this out quickly.